That's another exam walkthrough for you. This one is from Oscillations, and this is question 15. So let's try this one out. Okay, so here we have doctors can use ultrasound to monitor the heartbeat of a baby when it is developing inside the mother. A baby's heart was beating at 142 beats per minute. The wall of the baby's heart was moving with the maximum velocity of 22 millimeter per second. Calculate the maximum displacement in millimeter of the wall of the baby's heart. Assume that the motion of the wall of the baby is simple harmonic. So this is pretty simple. You're going to have x is equals to x naught cos omega t, okay, and then v is equals to minus x naught omega sine omega t. Okay, this x naught here is the amplitude. This is the maximum displacement. Now, they want you to find the maximum displacement, and then I've told you the maximum velocity. So if I plot the graph for velocity, it's going to look something like this. It's going to be a minus sign graph. Minus sine theta graph. And minus sine theta has the maximum velocity here, v, here, v. Now, give me a second. Now, if this is going to be your maximum point, so at the maximum point, okay, let's say this is time, and this is the time period, okay? Okay, one cycle, we are seeing one cycle, right? Then we have another cycle, then we have another cycle. So this is time period t. And this here is where the maximum occurs, which is t by 4 is where the maximum occurs. Okay, this is t by 2, this is t by 4, right? So t by 4 is where the maximum will occur. Okay, so what I can do here is I can say that sine, now omega is 2 pi over t, which is the time period, times t over 4. So just t cancels out and I get sine as 2 pi over 4, which is sine half pi, which is also equals to sine 90, and that's just equals to 1. So I can write V max is equals to x naught omega. Okay, now what I want to do here is I want to find, I know this is 22 millimeter per second, so I can write 22 millimeter convert to meter minus 3, and then x naught is what I want to find, and then omega. So to find omega, I can use this information of 142 beats per minute. So 142 beats occur in 60 seconds. 60 seconds. So 1 beat will occur in t seconds. So t is equals to t is going to be equal to 60 divided by 142, and that's going to be the time period. So I can say 2 pi divided by the time period, which I know is this, 60 over 142, and then I can find my x naught value, which is going to be, so you're going to get the answer as 1.479 times 10 to the power of minus 3, and then you're going to times it by 1000. So your final answer is going to be 1.479 millimeters. Okay. Right. Then we have the motion of the wall of the baby's heart only approximates to simple harmonic. State what is meant by simple harmonic motion. So this is pretty simple, so I just wrote it down. The resultant force is proportional to displacement, and the resultant force is in the direction of equilibrium position. So this is 2 key marks that should be very easy to get. So here are 2 spring combinations. The reason I'm explaining this is for the next question, guys. So the next question is a bit tricky, and you need to know about parallel and series spring. So I've put a video for the formula of parallel and series spring and how it's derived. You can check it in the link in the description. Okay, so I'm just going to write it down. When your springs are in parallel, So when they look something like this, okay, if you don't understand this, I recommend watch the video. It's just a few minutes. And when these springs are in series, your K total will be equals to K1 plus K2. And here, on the other hand, when they're in series, your K total is 1 over K total is equals to 1 over K1 plus 1 over K2. Okay? Right. So this is for both conditions. Now, if these springs are identical, then here K total will be equals to 2K. So we can say the K total, if your spring is identical, is equals to NK, where N is the number of springs. And on the other hand here, we know that K total will be equals to, wait, give me 1 second. So 1 over K total will be equals to K1 plus K2 over K1, K2. Okay? And when you flip this, you get K total is equals to K1, K2 over K1 plus K2. So then what will happen is your if your K is same, so K1 is equals to K2, the spring is identical, then you're going to get K squared is equals to 2K. This K will cancel out with this, you'll get K over 2. So we can say that K total, when your springs are identical and in series, your spring constant, your total spring constant is the spring constant of the individual springs divided by the number of springs n. So this is when your springs are identical and they're in series, and this is when your springs are identical and they're in parallel connection. Now, if you don't understand where I got this formula and this formula from, check the link in the description. Yourself first, and then I will tell you the answer. Okay. So a student hangs a mass of 0.22 kg from two identical springs as shown. So here we have two springs shown to us. Now they are identical and they're in parallel. So we just saw that if they are in parallel, then your K total is equals to NK. Okay. Now, give me a second. Okay. So she displaces the mass vertically and the mass oscillates with simple harmonic motion. The student measures the time t for the mass to complete 30 oscillations. She repeats this measurement. Her measurements are given in the table. The springs are taken from a box labeled 21 Newton per meter. So this is the spring constant of each spring. Okay, that's what the question says. Deduce whether the K value on the label of the box is correct. So you're going to take two springs of 21 Newton per meter and you're going to combine them together. So the total spring constant will be twice of this. Okay, the total spring constant will be 42 Newton per meter. So when we're going to use this formula, T is equals to 2 pi square root m over K. That's the formula we're going to use. This K is the total spring constant, right? Okay, so this is the total spring constant. Okay, I can derive it. I'll derive it at the end. Okay, at the end of this video, I will show you why this is the total spring constant as well. Okay, but right now let's assume it's total spring constant. Okay, now what I've done, I've squared everything and I've moved the 2 pi to the other side. So I've squared everything and I've moved 2 pi to the other side, and then I've done is I've moved my K to this side, and this entire thing I've moved it to the other side, and then I get this, and then this is my final expression. So K is equals to 4 pi square m divided by T square. How do we find T? Well, first you're going to find the mean of these values. You're going to add them up, you're going to divide them by 2, and you're going to get 13.675 seconds. Now this is the time taken for 30 oscillations. Let's find the time taken for 1 oscillation. So you're going to cross multiply. You're going to get this as your time taken for 1 oscillation, which is the time period. So you know the mass is 0.22 kg. You're going to plug that in here. Okay. And then you're going to plug in the time period value and square it, and 4 pi square. You're going to get your answer as 41.8 Newton meter. Now, I know this is the total spring constant, but I want to show you I want to prove that the spring constant of one spring, this is the total spring constant. What we got was a total one. I want to find for one spring, right? That's what the question tells me. The springs are taken from a box labeled this much, which means each spring is 21 Newton per meter. But this is the total spring constant. And we know K total is 2K. So I want to find that K. So I'm going to divide this by 2 and I'm going to get 20.8, which is approximately 21. Okay. So again, why is this the total spring constant? You can see at the end of the video. Okay. Now let's do the next question. So in the next part, we have the student attaches the mass to one spring, holds the other end, and then she sets the mass into oscillation by oscillating her hand vertically as shown. The student increases the frequency at which she oscillates her hand. She keeps the amplitude of oscillation of her hand constant. She observes that the amplitude of oscillation of the mass increases to a maximum and then decreases. So what we understand and what's going to happen now, okay, is that the person with the hand is going to cause the spring to oscillate. Now this spring has a natural frequency F0, okay, and then we have the driving frequency, which is the frequency of this hand, which is moving up and down with a constant amplitude. Now what's going to happen is the frequency of this mass which is oscillating is going to increase as it moves up and down. And then what's going to happen is that the frequency will increase, and it will reach a value where it's equals to the natural frequency. So the driving frequency is equals to the natural frequency. So when this mass, its frequency increases, and at a certain point that frequency at which this mass is moving with will be equals to the natural frequency. At that point, resonance will occur. Okay, so at that point the driving frequency should be equal to the natural frequency. Okay, that's what's going to happen. Okay, then what's going to happen after it goes past the natural frequency, the amplitude will decrease again. This is the amplitude. Okay, this is the A max. Okay, amplitude max. So the reason this happens is that when the amplitude is max, the driving frequency is equal to the natural frequency of the spring, the mass spring system. At that point, resonance occurs and maximum energy is transferred to the spring. So the spring's energy will be maximized. It will gain maximum energy and amplitude will increase. Okay. Now let's go to the next part. Now this is pretty standard question, so I'm not going to talk too much about it. It comes a lot, so pretty repetitive. The next one is a unique question. The student makes the following conclusion. As the frequencies increase, the amplitude of the mass increases to a maximum, so energy conservation does not apply in this situation. Explain whether her conclusion is correct. Okay, so now you have to understand one very important thing in resonance, and most people ignore this. In resonance, maximum energy is transferred, and if you watch my lecture video, I say that efficiency is very high. Okay, now let's say this is the mass spring system. Okay, and the hand here will transfer energy to the system, but the system will lose a lot of energy. Okay, so the energy output divided by the energy input times 100. Okay, now I'm giving some energy in and a lot of the energy is going out, so the efficiency will be a bit low. Okay, but what happens at resonance is that all of this energy is transferred from the hand to our mass spring system and very little energy is lost. So what happens is the energy output divided by the energy input times 100 is equals to efficiency. Okay, now a lot of the energy goes in, very little is lost, so the efficiency will be high. Okay, that's basically what this question is talking about. Okay, so what we have to say is that some of the energy is transferred from the mass spring system to the surroundings. So some of the energy is transferred there, and some of the energy is transferred to the mass spring system by the hand. So it gains some energy and then it loses some energy. Okay, so this word transfer is very important. You have to say transfer. Okay, transfer. Now at resonance, when the amplitude is maximum, the energy transferred to the surrounding becomes very less, minimum, and the energy gained by the mass transferred to the mass spring system from the hand is maximum. Okay, so using this we can understand what's happening, what's going on. Why does this amplitude increase to a maximum, right? It's because that the energy that is lost to the surroundings, okay, is minimum. So that's what actually happens. So energy is conserved in a closed system. So the student is actually wrong. Okay, so now I'll tell you why the formula of the time period had the K total. Okay, so here I have my spring 1, my spring 2, and I'm going to put a mass on them. So they're going to extend a little bit, and then, yeah, so both of them will have the same extension. So we're making an assumption, by the way, here. Well, not an assumption, but it's a specific thing that goes with when your springs are in parallel. Okay, so it's not an assumption, it's just a rule, like a rule that's always shown when two springs are in parallel, is that they have the same extension and displacement. Okay, same extension. So both of these springs will have the same extension. Okay, and so what you could say basically is that both of these springs will extend by the same amount. Now, if you see, the weight is balanced by two forces, F1, F2. So I can say F1 plus F2 is equals to mg. Now F1 plus F2 is actually just F total is equals to mg. And F total is K total, okay, times the extension is equals to mg. Okay, now, so extension here. Now, what I actually did here was, if you want a little bit more detail, is F1 is K1 E plus K2 E. So I can say K1 plus K2 E. Okay, so that's basically what I did here. So this goes here, okay, and becomes, so this is just K total. Okay, now if both these springs are same, identical, then these two combine together to make 2K. 2K is K total. Okay, so that's that. Now that's the first thing. First step. In the second case, we have mg is equals to the force total, and here mg is equals to actually we are accelerating here, so we are accelerating downwards, so we cannot say mg is equals to, we're actually accelerating. Okay, so we're moving downwards, we're accelerating downwards, so I'm going to take down as positive and up as negative. So I'm going to say ma is equals to mg minus F total, and then F total here is going to be K total. Now here we have extension plus X, okay, minus mg is equals to ma. Now remember, mg was just equals to K total times the extension, so ma is equals to, instead of mg, I'm going to put in this, so I'm going to get K total E minus, expanded inside, K total E, this is just the same E as well, plus, not plus, minus K total X. So these two will cancel out. I'm going to get MA as minus K, spring constant total X. Okay. Now the reason I took force total is because this mg is being balanced by these two forces, right? So I'm going to combine these two forces. And the same thing here. We have force from this spring, force from this spring. Both of this F1 and F2 are trying to oppose mg. So I'm going to put minus F total. Instead of writing F1 and F2, I'm just writing F total. And F total has these total spring constant, right? So F total is just equals to the K total and change in the extension, okay, or change in the length of the spring, okay. So here the total change in length of the spring was E plus X. Okay, now here we have this, so we can say A is equals to minus T over minus total spring constant divided by mx. I can compare it to A is equals to minus omega square x. So omega square is equals to K total m, and we know omega square is, I can square root both sides, square root. Omega is equals to K total over m. 2 pi over T is equals to KT over m. And then I get T is equals to 2 pi square root m divided by the spring constant total. Okay, that's why when we calculated the value of the spring constant, it was the total spring constant value, which is equals to nk when they're in parallel, and when they're in series, the K total is equals to K over n in series. So series looks something like this, and this is what parallel looks like. It's kind of like your resistors. When you have resistors, when they're in parallel, they look like this. When they're in series, they look like this. Right? So that's all.